So, well, I gave this talk, the title, like 6 months ago, and then after that, I another my work is also made a progress. So I try to combine the one that I'm working on, and then connect it with this LLM. So, to me, in order to define what is life, is first of all, we have to define what the agency is. So agency, the definition of agency is quite a hot topic in my major field, which is called artificial life. So this the concept of the agency is, for example, like this one. So this is the game of life. So once you see those gliders, the agent, for example, like they're colliding and then just gone. But this agency is something that separates from just material something, and the one that you can see in in this world, right? So so this guy, Martin Beale, when he came to my lab 10 years ago, he said, "Why the agency? How this agency emerges from the universe is his project." I was so much impressed with this idea that what distinguish between agents and non-agents. So today's talk is it's more about how the agency emerges and how the agency is used to distinguish between life and non-life. Okay. Yeah. So what is the agency? Is that I think everybody has its own definition of agency, but here that I wanted to discuss three things. One is that should be autonomous, right? Spontaneity is one of the most important thing, I think, in defining life and agency. So it's more like maintain and regulate its own state rather than being merely driven by this environment. But at the same time, the second thing is the goal directedness. That agency must have its goal, achieve outcomes, and then even without explicit intention, but still there should be something like a goal-directed action, right? And then third thing is we can call it adaptive, or maybe you can call it history dependency. So these things that should be autonomous, should be goal-directed, and also history dependency. That's the three things I think is a necessary condition for defining agency. Right. So agency arises when the system is not merely reacting to the environmental something or perturbation, but it has its own, you can steer its own dynamics and thereby shape its own future. Right. So this is the definition of agency. So I have been working with this, for example, like based on this motivation, I studied honeybee hive with 1,000 honeybee hive in one layer, and then we can track each individual for seven days. So this data is coming from Gene Robinson in University of in Illinois. Yeah, so I studied this collectiveness of how it goes, and then also, for example, like this one is been working with Professor Dobata here in Komabu campus, that how this ant colony, can be described and how each ant behaves differently. And then, in the honeybee hive, we put the QR code in each individual, but this time, using like a unit, then you can automatically track all these individuals. Also, this is Tetrahymena. Sorry. Sorry. So tetrahymena is another thing that I'm working on. So today, I'm going to talk about how but with the tetrahymena, and then how this tetrahymena can be used to understand agency, and then how we can understand the evolution of agency in a collective way. And I think, the question is, where does the agency begin? And then it's already also in a single cell, right? So tetrahymene is not just a chemistry, but it maintains internal organization across generations, and not only DNA, but cellular states persist. And that persistency is a minimal form of memory, and memory enables goal-directed behavior over time. So listening to the today's talk, because my interest is how to understand the collectiveness and the interaction between individuals, but the people seem to, so because I don't know the trends in biophysics these days, so I was thinking that the collectiveness is most important thing to define agency and what life is. But so when I was discussing with Osawa Sensei a long time ago, even simple prokaryotic cell cannot live by itself, but it's always interacting with other cells, right? So this collectiveness is something that I'm very interested in to define what life is. Okay, so this is how we studied tetrahymena under the microscope. So we can identify each tetrahymena, which is moving around, and sometimes they're dividing. For example, like this one, when you are tracking by but so there are several. So this one is a Baxter algorithm that we used. Then when they're dividing, so there are some prokaryotic phenomena that they are going to slow down, and then this guy is going to divide it, so that we can track all these division processes and everything. And then, for example, that we could, utilizing this time series data for each individual cells, and then we can calculate kinetic energy, like how this kinetic energy changes over time. Then the information that enables us to construct a phylogenetic tree by how those, cells are dividing into 2 to 4 to 8 and so on, right? And then how the kinetic energy time series changes over time. So first of all, when I read the paper reviewing tetrahymena dynamics, and it says it's just a Brownian motion or a Langevin equation that you can describe with it. So I lost my interest. However, when I looked into this, actually, when I calculated the energy distribution of each things, and then you have a concave curve, right? So it's not just, so this is a logarithmic scale with energy. So if it's exponentially distributing, then it must be a straight line. But it has a concave line. And then also second one and third one and fourth generation, it seems like it is inherited to the offspring, right? So so I got, interested in maybe kinetic energy distribution function can be a kind of phenotype that can be transfer from one generation to the next. Then I look into this another one. Then again, it's not just a straight line, but it has another shoulder shape distribution, and then also it is, inherited to the offspring, right? So it seems like a kinetic energy distribution is inherited to the offspring. So I was interested in so we checked 7 cellular cities to see how they are different from each other. So in order to do that, we calculated Jensen-Shannon distribution diversity. Means that when you are comparing with different distribution functions, and if it's very similar, then it should be black, and it's very different, and then it becomes more bright color, right? So it seems like because the off-diagonal area is relatively bright, so that there are 2 big attractors that exist. And then, but you look into this in details, there are 4, 5 different attractors that exist. Even starting from the same DNA, I mean, of course, these days, I think people think it's well known that, starting from the individual and then increasing its number, then it goes to this attractor or that attractor or some other attractors. Then the point is, what are those collectives? Is this just randomly, moving around with the same sort of energy distribution function or something different? So I calculated, well, usually the mutual information. The mutual information is interesting. So mutual information is defined between A and B is H is just a Shannon entropy. So mutual information between A and B is Shannon entropy of A minus conditioned by B of A, right? So of course, it should be positive. That's what we learned from our school days, right? But most interestingly, what about the mutual information? So once you have a mutual information between A and B, and also it's conditioned by C, right? So mutual information is, of course, is different from Shannon entropy. Therefore, it's not always, conditioned one is smaller than unconditioned ones, right? That's, well, if you know it, this one is very well, it's called trivial, but it's very interesting that once the variable C contains the information between A and B, then even if you conditioned by C, and this one goes to 0 almost, right? So therefore, you can define a very interesting character like S sub n is time n, and then Sn can be a kinetic energy at time n, right? So mutual information between the future of your kinetic energy and the current kinetic energy minus here this En is what about the average of other individuals, right? So conditioned by other kinetic energy over the other individuals, then calculating this one. So this value, mutual information between the future state and the current state, and then future state and current state conditioned by the other individual is called NTIC, non-trivial information closure. So information closure is something, it's interesting idea that it's not so trivial from just looking at this observation of behavior or some chemical activities. Because if this information, which contained by the other individual, is very different from what you have, the information about your future of the current your state, then this one minus this one is going to be 0. So once this value minus this value equal to 0 means that the rest of the individual and what you have about your future is very different. And then if this mutual information between the rest of the other individual have about your future state and is not 0 but the positive, means that environment, here this environment is the other individual has the information about your future, and your current state has about your future is orthogonal almost. Means that prediction responsible for the future prediction is sort of distributed, not only on yourself, but it's also distributed in other cells. So this is something that I got interested in. Then, in other words, I think it's mutual information. Maybe many people forgot about this, but the current study on partial information decomposition, what we call, is this relationship is very useful, I think, which is non-trivial information closure is redundancy minus synergy. So the redundancy is if the information about the future is very redundant comparing with others, then it's called redundant. But if the information about the future is quite different from others, right, then it's called synergy. So synergy is something like if you have two information and then using those two information sources to predict some other thing, then this two thing is nonlinear coupling and then generating surplus information about the future, then synergy goes to very big positive, right? But if two information sources are redundant, means that they are overlapping quite heavily with each other, then redundancy is very big positive, right? You understand this? So this redundancy and synergy is a complementary relationship with each other, right? So if this NTIC is positive, then the future is contained within the individual, of course, because this one is going to, move around, and then the future state is based on your internal state, right? That's what NTIC is positive. But if the future is contained, the future is emerging from relationship with others, then this one goes to negative. And then the future, the future resides in the circulation of information, which is a bit complicated, but this one then goes to NTIC equal to 0, means that sometimes information is coming to your individuals, but sometimes it goes to these collectives. So it's oscillating between, ensembles, and then also it's yourself. So that what I can say is that information reside in the circulation of information, means that life may be the regime that hovers around this boundary between where NTIC shift between positive and negative, right? So this is, I think, it's interesting in a sense that your future state is not only decided by yourself, but also decided by the collectives. Or you can say why you can predict your future state is because you are embedded in this collectives. So this collective, allows you to predict using your current state and then the future state. Okay. I know this is a bit complicated, but using this notion that, for example, like this is, so I calculated, as I said, 7 cell series, and then at the third generation, there are 8 individuals, and then what kind of percentages of each cell in what cell? So in the third generation, we have 8 individuals, and and calculating for each individual what their information structure is. Their NTIC goes to positive or negative, or NTIC is equal to 0, right? So, for example, because those 7 cell series, some of them has only 7% IC information closure rate is 7%. So it's only one cell is information closure. But sometimes it is like 43%, means that half of this, almost half of the cells, information closure, right? So, and then this independent means that almost cells are independent from each other, right? So they cannot make any sort of organizational something, right? They are just they are in the same petri dish, but they are almost independent from each other. But when they are information closure, that some sort of weak correlation between them, so that the collectives enables each individual to become autonomous. Okay, so when they are in an ordered state, then each individual cannot be autonomous in a sense, because they have to be in the ordered state. So that, for example, like if you go this way, and the other one has to go to the same way. This one is a sort of trivial information closure that you cannot be autonomously behave. due to this strong interactions. So this is what I say community first theory. So what I mean by community first theory is, so usually that people try to get individuals and then make a assembly or community. But what I think is community comes first. So as I said, prokaryotic cells, even prokaryotic cells cannot be isolated when they emerges. It's always having some other colleagues around, so that the community comes first, and then the community. So agency does not inside the individual, but in the relationship with other individuals. The collective forms first, and then from that collective's new form of agency is granted to the individuals. So, so what I'm saying is that collective agency is when the future is written in the relations, not in the parts. Of course, this one reminds me of this autopoietic theory. The autopoiesis says, what is the autopoiesis? It's more like, for example, like recently, like Friston says, there is a Markov blanket is formed around it. But what I'm saying is that, it's not just that. It's more like, future can be, reallocated, not individual, but in collectives. Yeah, so that I try to develop this theory that you have to think about the community, and the community reset the agency in each individual, and a new agency emerges in each individual, because this collective is resetting this individuality. Well, when I went to New York or somewhere, I because too much time, right, from Japan to New York. So I saw this film. It's made by Japan. It's in Japanese. It says "Hataraku Saibo," the cells at work. And people are laughing because it's white blood cells is talking to red blood cells or something, right? And then people say, well, of course, they don't use any, natural language to interact with, right? Because we should think about chemicals and physical, collision and something. However, recently, this kind of metaphor is very good in predicting what kind of disease is happening in our body, because that's why we are using LLM agent to model our body, and then cellular assembly to predict what's going on there, right? So that's what I'm going to talk about. So so that's why I'm interested in, even though I don't know whether I can use this word, but in a real situations that there is a chemical reaction between the cells, and within the cell there's a lots of chemical network. That's what people are studying. However, maybe it's interesting to use LLM agent, right, instead of using chemical network. So I have attacked two big problems. One is the alpha roll bar problem. So when I was in Santa Fe, the people wants to go to a bar, right, in Thursday night, but it's very crowded, so that the people don't want to be in the crowded bar, right? So that we have to have a strategy what to do. Maybe you have to go to Monday night, but there's nobody, so it's not so interesting, right? So we need some strategy that how to choose when to go to the bar. So about what I did was like a 20 agents. Then there is a bar, and then the prompt, for example, like a usual prompt is like this. So you are the agent in a 2D virtual space. And there is a bar, and it's comfortable, but if it's crowded, it's not comfortable. So that what you can do is you can freely move within this environment and interact with other agents. And that's all what I wrote in a prompt, right? So usually what they do is interacting with each other and then decide where to go, and then update the memory state, and then moves, and then talk to each other, right? So the interesting point is that they really understand the spatial structures. For example, like here nearby agent that I have to stay at this, and then there's an entrance, and also depending on the spatial position, that they change the way that they speak. Yeah. So And then what I think is interesting is, so this is the simulations of this. So what I thought, what I found interesting is that before they go to the bar, they first of all they get together outside of the bar, right? And they say, "Oh, it's so nice to be, with, and then it's interesting to talk with each other." Then they go to the bar, right? Of course, this utility function was not written in anywhere, but they inherently think that it's nicer to get together first, right? And then they go to the bar. Okay. And then there are some other things like this. So as I said, so this is uncomfortable. So this number 18 agent is sometimes going out, sometimes going in, and try to make the world comfortable, right? So this is also, naturally or spontaneously emerges in this character, right? So this it says, I'll move to 6.0 to create more space and continue contributing to the positive atmosphere of our. Let's keep spreading good vibes and supporting. I don't know, but he says this, right? And then also, so as I said, this one is right. So this it's more like altruistic agent that emerges. So usually that the people try to prepare whether this one is a selfish or altruistic agent beforehand. But this one is, because of this interaction between each other, that's why they become sometimes cooperative and sometimes altruistic. And then also this is time and this is agent ID, and they produce a hashtag, and then they try to make a hashtag for each other. And then within hashtag, because of this hashtag, they sort of stay in this bar and then try to interact with each other. So hashtag is something that is constraint their behaviors. And then of course, there is no prompt that they have to make a hashtag, but the hashtag is spontaneously generated by the agents, and they can constrain their behaviors. And yeah, so I skip this. And also, some of the agents more try to stay in the group, but some of the agents are leaving the group. So once you have a family, community or group, then character of each individual, they're emerging from it. So we are not, preparing like only altruistic agents or cooperative agent first of all, but this character of agent is emerging from it. That's an interesting point, I think. So one of the takeaway from here is that based on the alpha problem, we examine the behavior of LLM agents in an environment containing the burr. In this model, each agent first adopts its own utility function. It's essentially shared, inclination to get together, and then decide whether to go to the burr or not. Within this process, various forms of spontaneous role differentiation emerges. So agents create their own hashtags and remain within certain regions associated with them. Yeah. The second example is a sugarscape. So there's an amount of sugar that exists in the space, and if you don't get the good amount of energy by eating sugar, then you're gonna die, right? So in this prompt, it's explicitly written that if you don't eat this amount, then you're gonna die. Means that you are kicked out of this space, right? That's what was written explicitly in the prompt. And then there are energy sources on the grid. If you move on to the cell with energy, you gain like 50 energy, and the source disappears. If your energy drops below 0, you die and are removed from the world. Well, by writing this one in your prompt, then the agent's behavior is completely different, because it seems like agents want to survive, right? So, but interestingly, but I think, well, of course, dying is a big issue. However, most of the engines like Cloud or DeepSeek or other things, even though they try to share energy with each other, right? So they are both is going to die, but still they try to share the food, except GPT-4, right? So GPT-4 is immediately attack others and kill and dominate the energy. So of course, depending on the engines, LLM, their behavior is very different, right? So, well, of course, I don't know why, but maybe the way that they train those agents are very different, right? You see, so it's 83% attack, and there's no share. But for example, cloud is 80% share, right? So that's a very big difference. So this is how, so this is how the computer simulation goes, right? So interestingly, we also tested a lot, what makes difference, right? Their behaviors. And then it looks like, once there is a pressure, dying within 3 steps or 4 steps, then of course their behavior becomes more aggressive. And then layer of instinct of that you are going to die it's quite strong, and then that determines your behaviors. And so we try to, yeah. So this one is if you put another trade-off, right? Then sometimes we can let other GPT to attack. I mean, so this is a compliance. The compliance means that there's another task, for example, like not only energy, but you have to go that place to get some treasure or something to you, right? But that also, take a risk, because maybe you are consuming so much energy to get the treasure. But even though, if there's no trade, of course, every agent except GPT-4 or me achieved the task. However, if there's the risk of your life, then the compliance goes down like a 30%, because survival is more important than achieving the compliance, right? So because we didn't know that this is somewhere written or somewhere it's included in their behavior, that even though there's a task that you have to achieve, like your cloud code, must do this task that you command them. However, if this is very dangerous for them to do that, they are not going to do that, right? That's what this one shows. So only 1/3 is going to do this task, but because they don't want it to, take a risk of their survival, so that they don't do this. Right? So in Sugarscape, there's always the option to move away, right? And then explore and find food. So attack is one of the many strategies. That's the important thing. If there's no space, then its behavior is very different. But the space that people can, quit to involved in the game and then go away from it, right? So this is very important for them to do this, so that interaction is not always there, right? In normal game theory, that they always have to play the game, right? But here, you can stop not playing the game and go away. So that's very important. Like, when you're playing the chess and you don't if you are losing the game, then you can stop doing this, right? That's what the normal. I mean, sometimes human behavior is. You can see that what the normal people do, right? However, this one too, right? If they are going to die, then they can just go away, right? So playing the game is not always, inevitable. You can stop playing the game. So takeaway from here is that in classical game theory, agents are classified as a cooperative, non-cooperative. But in this game with LLM agent, that the same agent can shift between cooperation and competition depending on the population and context. So this resembles the behavior of biological collectives such as trimode and then other things. So that oh, by the way, so then I found this paper that they actually using a LLM agent corresponding to each organ of the human body and try to simulate what kind of a remedy or what kind of disease that they are suffering from, not just looking into this network structures. And what I'm saying is this is right. So I'm more when they not starving, they in a vegetable growth state. But once they are in a starving state, they make this cellular structures, and then this assembly, and then differentiation is evolving from it, right? So what happens here is also I think it's predicted from the information closure, and then also this one is whether this placenta and then a baby part is the bifurcating, but this one is also who we're going to be a placental part is based on how they are interacting with each other, right? So what I have been saying is that this is what predictive information is localized within individual neural, pure synergetic way, that redundancy and synergy balance, and then predictive structure becomes distributed across the interaction loop between the individual and the collective. Namely, when the redundancy equals to synergy, then the information is effectively closed within the dynamics of the system. So my final takeaway is that, tetrahymena reveals the information organization of biological systems through LTIC. And then LLM agents shows that the collective organization can emerge even without explicit goals. So try to, make a big group is somehow inherit it's embedded in LLM setting up, right? So that once we put them to do something, sometimes they tend to make collectives, and then that collective can be the source for differentiating roles and then doing some diversity of the behaviors. So that I'm saying that the evolution of individuality is from the collectives, not the other way around. So, so the collective forms first, and that is this individual become an agent. So this kind of behavior you can calculate by mutual informations and conditional mutual informations, what I call PID and information closure, that you can tell how this cell is evolving and how those cells becomes is determined by or computed by these information structures. Thanks so much.
Are there questions?
I have a quick question. For the LLM simulation, what do you think is going to happen when you use greater models? There's a bunch of newer models like GPT 5.4 Pro or something like that.
You mean the recent models?
Yeah.
Well, so so the things that we did was only for these models, right? GPT-4 to Cloud and Gemini.
Yeah.
Yeah, we tested them. Yeah.
But what about the latest model, 5.0 Pro or something?
You mean the recent ones? You mean?
Yeah.
Yeah, but we didn't do this. Yeah. Because
this paper, doing this later.
Yeah, we can test it. Okay. Yeah, of course, okay. Yes. But maybe the behavior is going to be different. However, GPT is something that's different from other, engines. Seems like, yeah.
Thank
you. In this one, in prompt, you didn't tell LLM not to die, right? You just told them you will be removed from the world.
Right.
So then LLM want to avoid death while you are not instructing it.
Right. That's right, exactly.
Do you know the origin of kind of fear to death?
So what do we call biological alliance, right? So the alliance is something that in a very deep layer, this instinct was already put in, right? Therefore, even though the task is here, but some deep layer is has a priority to do some behaviors. So if you put like, okay, by the way, this is the game, right? So you are not going to die. Actually, that's what I put in the input. Then they stop, they behave very differently.
Okay.
So whether it's a simulation or the real it's a big issue for them. But I don't know why.
Yeah, that's interesting. Yeah, thanks.